in a nice comic style, but I'm still improving my prompt engineering skills. So let's just go plain text. It happens, I think it's 6 years ago with my manager. So he asked me, hey, maybe we should fuzz the Linux hit driver. That's under the context that we're talking about USB attacks. And any idea how to do that? At that time, well, if I were an experienced kernel hacker, so I'll probably just go with the scholars. But I know nothing for kernel fuzzings. So the actual me is I just finished Userspace fuzzing with libFuzzer. So, oh, I can do this. Just take a look at the hit core.c. It's just a plain C file, right? Let me just throw it to clone, and with fsanitize equals to fuzzer, and then I mock all the kernel APIs. Let it run. And of course, clone slapped my face with 100 error messages, and with the last error messages, too many error messages. So I was struggling on that. And then my coworker, Matt Alexander, well, he already left Google, but he talked to me, hey, I heard you want to run kernel code in Userspace, right? You should try LKL. So that's how we started this conversation. Thanks, everyone. So I'm Xuan Xing. I'm the manager of Android Red Team. This is Eugene Rodionov. He used to be our tech lead, and now he's leading a different team, device and platform security. We worked together on the LKL fuzzing for a while, so I'll talk about that and share our learnings. Here is our agenda. So we'll have a brief intro of the team, and then talking about the basics of LKL, and how do we add the fuzzing support of LKL, and then talk about a couple of fuzzers that we created and the bugs we found. We'll try to make quick demos. I'm going to do some not really risky live demos, but hopefully demo god will work this time. And then we'll have short conclusions and Q&A sessions. So who are we? So we are Android Red Team. Well, he used to be.
No more kernel hacking for me.
But yeah, so our goal is to protect Android ecosystem through like offensive research, and we have multiple approaches to do this. And one of the very important one is to scale through the tool development. And one of the tool is continuous fuzzing. So we want to run tools continuously in Google's infrastructure so that new codes can also be checked, the regressions can be discovered with fuzzing. But what is LKL? LKL stands for Linux Kernel Library. It builds Linux kernel as a user space library, so you can call all the kernel code in user space. It implements as a Linux architecture. This is not a new concept. There's some other project like User Mode Linux does similar things. But we choose LKL because it's more flexible for our goal. On the right hand, you can see there's a diagram showing the very high-level overviews of how this works. At the bottom, we have a host kernel, whether it's Linux, Android, or Windows, doesn't matter. But there's a shim layer in LKL providing the host environment APIs to the Linux kernel code. And the kernel code itself is all compiled into a library and linked with this LKL syscall APIs, which exposes the functions to the applications. From the applications, you can call these APIs just like you were operating the Linux kernel. And then that's how it works. So with this one, you can run kernel code without launching a VM. And we think this can work for kernel unit testing and also fuzzing and many other fun stuff. But we're going to focus on fuzzing. It's very simple to use LKL from your C program. You just link the library, and then you call start kernel, gives the host operations. And then you mount the file system, like sysfs, procfs, or other fs you need, and open your device node that you want to interact with, and issue command. This iocto actually calls the iocto handlers inside of the binder drivers. And in addition to that, we also added a couple quirks to support some LKL unique stuff, like we added MMU implementations. By default, there was no MMU because there's lack of hardware. So we, inspired by the UML, we add MMU implementation using the host's mmap functions, so we can provide different physical pages to virtual addresses. The other thing that we added is to emulate multiple processes. By default, when you run the LKL-based applications, it runs all in one single host process. That means all the kernel threads have the same TGIDs. So we implement a custom API to modify TGID to simulate that you have multiple kernel processes running. Applications. There are a couple of built-in applications in the GitHub repos, the FS2tar, CP2FS, LKL fuse. They are all interacting with the file system images using the kernel file system code, but without running in root privilege. And for fuzzing, so we are not the first using LKL fuzzing. There are already a couple efforts doing that. It's worth mentioning the first one that I actually run into when I search LKL fuzzing. I'm very sorry, I don't know how to pronounce the project name, but it basically has a collection of kernel fuzzers using LKL in Userspace. This person implemented the libFuzzer as the first one with LKL. He implemented, I think, fork support with libAFL, and it worked relatively well. There are other projects like Janus fuzzing the file system, and also we added a couple sample fuzzers into the LKL repos like hid or binder. There's also some quite interesting ideas, like, okay, somebody was running Linux kernel on JavaScript directly using LKL. I don't know how that works, but looks fun. There's also Userspace TCP stack by using LKL to run everything in Userspace for better securities. Unfortunately, I feel that these two projects are outdated for quite a while. I haven't seen any updates, so I don't know if they're still actively maintained. There might be more. I didn't search a lot for that. So from here, I'll pass to Eugene talking about how we enabled fuzzing on LKL.
Thank you very much, Xuan. Hello, hello. All right, so as Xuan introduced LKL, right now we're able to build a kernel as a Userspace library and run it as a pretty much like a regular Userspace code, like in a single process without any other additional overhead. And it means that we can approach fuzz in Linux kernel pretty much in the same way as we are approaching fuzz in Userspace code, and we can rely on the same tooling for debugging, reproducing crashes, for continuous infrastructure. Like for instance, we can use regular GDB debugger to debug and reproduce crashes in the kernel. On this diagram, we provide a high-level overview and flow of fuzzing using LKL. The left part of this diagram essentially includes a Linux kernel built as a Userspace library. We have a code under test, which is enabled via kernel configuration options. Or in this case, we can see that we are enabling binder device driver. And additionally, on top of that, to make debugging and detection of crashes more reliable, we enable KSAN, kernel address sanitizer. This is an architecture-specific feature, so this is something that we needed to implement for LKL. In this implementation, we are relying on a generic implementation of KSAN, so we are not using any hardware-assisted like sanitizers. We're just simply rely on the compiler-enabled instrumentation, which basically allocates shadow memory and instrument every memory load and store operation, as well as like bulk memory copy operations. And this is the first part of the fuzzer. The second part is actually the actual fuzzing engine. In this particular case, we're hooking this up with libFuzzer. There is no particular reason for using libFuzzer. I think pretty much like any Userspace fuzzing engine would work here. It's probably because we had a great success of applying libFuzzer for fuzzing Userspace code. There is a nice, well, when we started to experiment with this tool, there, like Google's continuous fuzzing infrastructure was heavily based towards libFuzzer, so we enabled it, and it works really nicely when you have source code of the target. It basically enables us to get fuzzing code coverage, and this is coverage-guided fuzzing engine. And we have this loop where libFuzzer generates fuzz data, which we send to LKL, execute a sequence of syscalls, and then gather code coverage and detect any crashes. And again, like for the code coverage here, we're not relying on kcoff solution. we're relying on the libFuzzer instrumentation solution to get information about which instructions we hit and additional information about, like, for instance, some magic values which are used in the compare operations to feed it back into the in the fuzzing corpus. And this enables us to build high-performance Linux kernel fuzzers, which are very scalable because, again, like the fuzzer is just a single process. We can take advantage of high-performance x86 cores. This is something that we've been playing with, and this is what I think LKL works for. However, I don't think there are any limitations for building it for other architectures such as ARM. It's just like we used x86. Additionally, it enables hacking with kernel. Well, maybe somewhat easier. We can mock hardware using PCI implementation in LKL, Virtio subsystem, which we'll cover actually later in this presentation, and maybe do some modifications with the scheduler. However, well, this is definitely not the perfect solution. There are some limitations. First of all, LKL doesn't support SMP, so basically it assumes that there is one single virtual core on which all the things are running, and this limits a class of bugs which we can catch and reproduce with this fuzzer. So basically, certain types of race conditions would be difficult to identify with this fuzzing approach because, well, LKL supports multi-threading, but it is more cooperative multi-threading, where a thread should yield execution to another thread when it's being blocked on something by acquiring mutex or using other synchronization primitive. There is no preemptive concurrency in LKL because of missing SMP support. There were some challenges with their getting the build. The binary size was getting a little bit problematic. Well, 15 megabytes right now, I think these days is not a problem for the Userspace binary, but this is only particular for the version of the binary which has code coverage instrumentation enabled for getting line coverage information. Basically, you're understanding which lines of code were hit while reproducing the test case for visualization with such tools as kickoff, as code coverage, gcoff, I'm sorry. Again, like currently we're only working on x86 x64 architecture. However, nothing seriously limits us to apply it for other architectures, ARM. And right now, as we're basically building some code which is intended to build on ARM platforms for x86, obviously we might hit some false positives or false negatives. Like, for instance, accessing unaligned pointer on x86 is never a problem, but on ARM this will create some issues. We need to mock low-level interfaces if needed. However, this is actually not a limitation, it's a feature. And later we will show how we're actually mocking these interfaces to be able to fuzz the kernel code which interfaces with the untrusted hardware. So basically this way we're able to fuzz test the kernel code which might consume untrusted input and process untrusted input coming from the hardware. And this project is not part of the mainline Linux, so this is a fork, and this makes maintenance of this project a little bit more difficult. And with that, I'm passing it back to Xuan.
Thank you, Eugene. Yeah, so now let's just have a quick look of the LKL fuzzers that we worked or created. So the first one is the human interface device, or HID fuzzer. This is more like a sample fuzzer prototype, just to show that, okay, it works, and verifying the case and code coverage all works. And the second one is a real business, is a binder fuzzer targeting Android binder drivers that the team have developed during our binder engagement. And last one is a driver that, as Eugene mentioned, a Virtio driver, trying to use this one to fuzz the Android pKVM with special attacking scenarios where the host is compromised and one guest supposed to be maintain its integrity. And with this one, we can fuzz the Virtio-based device drivers. Let's talk about HID. So this happens when we look into the USB attack surfaces. The scenario is basically when someone has a physical access to the device. Some are on purpose. Some are like malicious, like juice jacking devices that will plug in unknown USB charging cable to your phone. What can happen? And the target is the Linux heat system because heat is actually one of the big category of USB devices. Talking about heat, I don't know if anybody has looked into specs. I just opened the document and I closed it immediately because it's just too long. I didn't even want to look into it. Yeah, but on the right hand, you can see we have a very, very simple diagram. We have user space, we have kernel, we have hardwares. The USB stack, PS2 stack are the ones connecting hardware versus software. And we bypass those two hardware stacks. We use the user space head, UHead driver to inject head event. The fuzzing is because we are trying to targeting hardware attacks, so requires basically no user side interactions. Basically, mostly happens when the hardware enumeration phase happens. So when we inject device descriptors, how the heat core responds to that. And this is inspired, again, I mentioned Bdush, whatever. I don't try to force myself pronounce the name. Fuzzing project is a proof of concept to see how we can support it. And this fuzzing project uncovered 2 bulletin class issues. They are all fixed long time ago. And there are more stability issues, mostly are not on the references. And one thing that I want to mention is how we verify the issues. Because we are bypassing USB and PS stacks, we don't know if the issue are legit, maybe they're triggered by some unknown effect. So what we actually did is after we find the issues, we use a special hardware called a phase dancer. Not sure you know that. It allows you to emulate USB devices. And we program the phase dancer to be a heat device and then use the same test input created by the fuzzer and pipe it into the hardware and verify the issue reproduces on real Linux device. That's how we verify it. So all the issues reported here are legit issues. We didn't try to exploit the heat bugs. However, there's a very nice talk published a couple of years ago by a couple of researchers here. They're talking about how to practically exploit heat device issues. And one of the author, Martin, is actually now part of Google and working very closely with my team. Let me show a demo here. As I said, I'm going to do a live demo, so we'll see how it works. I'm not going to do a lot of fuzzing. So the build part, I'll skip that just because building takes too much time. Here I already built my fuzzer. So you can see we have 2 fuzzers. Is the text big enough? Okay, so this is a regular heat fuzzer that's about this size. This is the one that with source code coverage information. This is the one that I mentioned. We have 500 megabyte binaries, which is not a big deal anyway. So if I run this one, just like regular libFuzzer, if I run it, I'll load the kernel and start running, start fuzzing. It's going to take some time, especially when it doesn't give it a starting point. But you can see at the beginning we have something about 1,000 executions per second. This is a really great performance for fuzzing the kernel driver features. When I prepare these slides, I let the fuzzer run for the one night. And I think it finished in a couple hours discovering the issue that I reproduced. Basically, we have an issue reported. I revert the patch so that the issue is still there, and it was able to rediscover the issue in just a couple hours, which is captured in this crash. So if I run this one with this file, and you see it crashes and gives very nice information about the call stacks, why it's crashing. There's the memset operations causes the write access. And this is the descriptors that we send to the kernel. And what's nice is now, I can hook regular GDB and debug this issue. And it shows, so this is a patch that I commented out to reintroduce the issue. And I can use whatever GDB command to show why is the problem. So here we have a report. It has a size to 0. And when the size -1, it creates an overflow. And then this causes this memset to write memory beyond the buffer size. And I think this is the benefit of running LKL in Userspace. You can use all the Userspace toolchains to debug the issue and work on the issue. Another thing that I want to show is, again, with this approach, I was able to generate Userspace-like coverage information reports. Let me make this bigger so that we can see it. This is top level under the heat, and what I want to show is the heat core here. We have the nice coverage rendering information here, like shows which line is executed, which line is not, because I only run this for 2 hours. So there's still lots of lines not covered, but inside of Google's continuous infrastructure, we have the libFuzzer running all the time. It has reached pretty much, I think it's 80% around coverage rate. Pretty much covers this entire file. And what's worth looking at, lots of hit device code is not covered here yet. Again, this is because I didn't run it long enough. Eventually, they'll get a little bit of coverage, but I cannot cover all of them. I think there are some of the device drivers require special setups I haven't figured out yet. But we get some coverage for the individual devices as well. And this is another benefit of having Userspace fuzzer. You get all this nice benefit. Yeah, with that, so that's our demo. Sorry if this is disappointing, but let's get back, and at least there's no crash. Oh, there is a crash. So from here, I'll pass over to Eugene talking about the real business, binder driver fuzzing.
Actually, well, why heat is not real business looks like quite scary.
Well, it's a prototype, right?
All right, yeah, let's look at the binder fuzzing. Earlier this morning, Case Cook hinted a few times that binder is one of the troublemakers in kernel, and in Android specifically. I think a source of exploitable, unfortunately, vulnerabilities which enable privilege escalation, getting root on the device, which work quite universally. Quick refresher, basically binder driver is a keystone of the IPC framework on Android. On Android, every application is running in its own sandbox, and pretty much the only way how they can talk to each other is via binder. For that, binder implements a fairly complicated protocol, including transactions, passing file descriptors, complex nested object structures containing pointer, and since it is at the core of the IPC, it needs to be so efficient, and any changes, and it may result in significant regressions in the performance of the device. So that's why this code is heavily multi-threaded, optimized. I think we did offensive research on this, and this is probably one of the most complicated parts of code we looked at the Linux kernel, because it's so dense. As I wonder how developers maintain it. So, well, anyways, here is the rules of the game which we try to follow. Essentially, what do we try to do? We try to fuzz binder driver with our fuzzer, hoping to find memory corruption vulnerabilities in binder and fixing them. So basically, we're assuming that we are running in the context of the untrusted application, and we are issuing ioctls to hit the vulnerable code. It's notable, when we looked at the binder code, I think it has maybe 4,000 to 7,000 lines of code. And if we distribute all the vulnerabilities historically reported in these components, we get about 3 vulnerabilities per 1,000 lines of code, which is a pretty high density. And the sad thing is that a large amount of them are exploitable. All right. Well, binder has been fuzzed actually by Cscholar for some time, and Cscholar found vulnerabilities in it, like I think bad binder vulnerability, which was publicly disclosed by Google Project Zero, which was used also in real targeted attacks in the wild. It appeared, then we started doing analysis. Cscholar actually found this bug quite some time ago, and yeah, so basically there is some baseline coverage. But we started to look at the coverage, I think we were not happy with how it was covered, around 30% or something. And we tried to understand how things can be improved and what is the reason for this low coverage. Looks like this communication protocol which binder utilizes is one of the reasons. Like there is a lot of data dependencies, complicated nested data structures which are being reshaped, scattered, and gathered together, which requires some additional handling by the fuzzing harness. So basically, just simply relying on the coverage, on the structure where fuzzing won't help here. Additionally, there are some state dependencies because this is a synchronous IPC. For instance, if client A sends a transaction to client B, client A cannot send another transaction to client B until client B actually responds back to client A. And this is one of the assumptions which we needed to take into account because just spamming one client with transactions simply won't work. They will be rejected. There is, again, some additional dependency on state. For instance, here we can see that in order to execute successfully ioctl with BC free buffer, which basically frees binder buffer, we need to previously execute ioctl number 1, which actually sends binder write-read transaction. And the buffer which we are trying to free, Y, is actually embedded in the ioctl number 1 as buffer field nested here. So this is some additional challenges. And a third one is binder implements multi-process coordination. So there is a special role called the context manager, because for two endpoints to be able to talk to each other, there should be some protocol. They would need to exchange nodes and references to establish communication channel. And the context manager is essentially a central directory which enables two clients to talk to each other, because context manager is always accessible at handle 0. And when a client starts, it sends its identity to context manager. And then context manager can redistribute those identities to other parties so that they can start peer-to-peer communication. This is something that we are also incorporated in our fuzzer using LKL. And we also enabled a libprotobuf mutator in order to add a structure-aware fuzzing to our coverage guidance in addition. So basically, we outline the grammar of the transactions using the protobuf messages and rely on the libprotobuf mutator to mutate those messages to emulate transactions with all the necessary properties which we want to enforce for this communication. And we implement 3 communication clients, client 1, client 2, and client 3, one of them being context manager. And in addition to that, while playing with this tool, we also wanted to experiment with some project which attracted our attention. At Black Hat USA, Ned Williamson from Google Project Zero presented an interesting research on concurrency, on how to deterministically discover race conditions. Because discovering and reproducing race conditions via fuzzing is known to be non-deterministic. Because like one thread is running, creates some special state, and then if a second thread is being executed at the same time, it can trigger this condition. And for instance, we can catch report using ASAN. For instance, this is either use data free or out of bounds memory write. However, when we will try to reproduce the same test case second time, it might happen that just those 2 threads will not be scheduled exactly in the same way as they were scheduled while the fuzz ran. And as a result, we will miss this window, and the fuzzer will not be able to reproduce this crash. So basically, reproducing race condition is not deterministic, and we really wanted to address this gap using LKL. So basically, we modified the scheduler to implement deterministic scheduler, meaning that it's seeded with a random value. And once it's seeded with a random value and the same fuzz input is provided to the fuzzer, it will schedule threads in kernel exactly in the same deterministic way every time. So basically, the thread interleaving will be the same. Of course, LKL doesn't support SMP, so certain operations won't work. Like for instance, the spin locks, they are compiled out. They simply don't exist in their no SMP systems. We needed to do some hacks to actually keep them there for Binder specifically, but in general, this won't work. But other synchronization primitives, mutexes, they work well. And with that, we got our fuzzer, we bumped our code coverage to 68%, and most importantly, we discovered 2 vulnerabilities which were fixed, 2 exploitable vulnerabilities, which were interesting. This has actually reinforced my faith in fuzzing after that. So, for example, looking at the test case. Yeah. Right here is, for example, a test case generated for the fuzzer. So we can see that this is a protobuf message, and it has 6 ioctals. These ioctals have a client, which represents the client, which is actually sending this transaction to the binder. And this is how this looks like being generated by the fuzzer. So I think it took quite a while for the fuzzer to actually come up with this specific sequence of 6 steps, 6 transactions in this specific sequence to introduce misconfiguration in the state, to manipulate with the reference counter and result in one object being freed, and then basically reading this freed memory, which was caught by KSAN with the KSAN sanitizer. All right, so I think this is it for binder fuzzer, and this fuzzer is upstreamed to your LKL GitHub repository. We'll provide a link at the end, and it's also run on Google Continuous Fuzzing infrastructure to keep finding bugs. All right. Moving on to the next project, which I think we also had quite good success with fuzzing LKL, is fuzzing Virtio front-end drivers in the Android-protected KVM. So our Android-protected KVM introduced like virtualization framework on Android devices a few years ago. The interesting property here that in a traditional KVM, basically, traditional KVM isolates the main host kernel from the guest VMs, so that misbehaving guest VMs, they cannot do any damage to the kernel. However, in Android protected KVM hypervisor also isolates guests from the host. So in case the Android kernel is compromised, the device is rooted, this protected KVM guarantees that whatever runs in this protected VM will be safe from misbehaving kernel. So yeah, essentially, it's essentially enforced by the hypervisor. And when we started to look at the attack surface of this protected guest, because we had in mind that we as attackers, we compromised host kernel, we run arbitrary code there, and we really want to break into the guest VMs. And hypervisor protected KVM doesn't allow us to do that. However, looking at the software stack running in the protected VMs, we found that it relies on the Virtio drivers in order to implement storage, in order to implement. There is no network, so basically storage, console, and other devices, which we'll show on the following slides. And there is a Virtio backend driver running in a cross VM, which is a virtual machine manager, and there are Virtio frontend drivers running inside guest VM. And essentially, we're interested in finding vulnerabilities in the guest VM so that we as attackers running the host kernel provide some malformed garbage data to the front-end drivers, hoping to trigger some memory corruption vulnerability and get code execution inside guest kernel. So this basically enabled us to emulate the misbehaving hardware to fuzz that part of the kernel which consumes data from it. So we're looking at the Virtio driver stack. We have on the left-hand side, we have cross VM virtual machine manager running backend drivers. On the protected guest VM, we have at bus layer PCI bus driver and the Virtio bus driver. We have Virtio PCI devices supporting both modern and legacy configuration. Obviously, ring driver with packed, split, and indirect modes. And for the device layer, we have console, we have block device, we have file system, and VSOC drivers. And essentially, the blocks covered here in green are something that we fuzzed. For the ring driver, obviously, we were trying to target the ring processing functionality. So basically, you're manipulating with metadata of the ring buffer, available read used fields to force front-end drivers to read out of memory. For PCI, we essentially mutated PCI configuration space in order to see like what happens if we just come up with some spurious PCI device with weird combination of resources and if there is something bad happening there. And for block device, we have a Virtio block configuration block data, which basically describes the parameters of the block device. This fuzzing effort resulted in a few issues. I think one of the interesting ones and impactful was found by the Virtio block fuzzer. Here we have essentially the fuzzer reported an out-of-bounds write on stack. So here we can see that there is a local array of fixed size. I think max buff per page is about 8. And there is unbound while loop where the only condition which controls when we should be exiting is the last part of the loop, because the previous one we're just bumping up the indexes. And the fuzzer was reporting that we are consistently writing out of bounds in the ARR array. While root causing this issue, it was actually interesting. While root causing, here's what we found. The fuzzer generated block size of this value. Obviously, this is not possible because the block size should be 512 bytes and going higher, like probably there is no block supported less than 512 bytes. However, there is no verification checks on the block size. When this block size was generated by the fuzzer, this resulted in their iBlock bits set to 32 in the iBlock bits field. And then we are shifting one, which is integer, by 32-bit lefts. And yeah, again, as Case mentioned this morning, there is a lot of fun with C-undefined behavior. Like when we shift one 32-bit lefts on different architecture, it can have different results. It was really non-intuitive for me to see that if, like on x86 architectures, you take one integer, shift it 32-bit left, you will get one again. Like on ARM, it is 0, like as naturally we expect, because this one will got pushed out like from the integer, and you will get 0. For x86, this is 1. And this resulted in a very interesting, result here. When we called create empty buffers, we're shifting 1 by this amount of bits, which represent the block size of the Virtio block device. And in this case, it will get value 1. Means that we have a Virtio block device whose block is exactly 1 byte. And as a result, we will allocate 4,096 buffer head structures because we will divide the size of the page by the size of the block. This is how the previous array is computed. And instead of value less than 8, we got 4,096, and this is how we're basically writing here some extra values. So yeah, that was really fun finding and really nice root causing, and also very interesting learning about undefined behavior of C compiler and x86 architecture. Yeah, I think we're about to hit the conclusion.
Yeah, I never thought 1 over shifting, but it's a little bit to get a 1. Okay, yeah. Well, conclusions. During all these projects, there's something that I learned. I figured this can be shared with everyone here. Is that first, technically, LKL can be a very effective way to fuzz certain kernel scenarios. That including, for example, you have complex setups, all hardware to kernel surfaces. Or if you want to use, for example, libprotobuf mutator or other Userspace libraries, apparently. And lastly is that, well, actually, the third one is that having access to Userspace toolings like code coverage, debugging can be very helpful. and it's always good to have alternatives. And the second one is for my personally is like, okay, the fact that you don't know something might be your advantage. Because of that, you will discover new approaches from very naive ideas, and you will learn without predefined mindset. I also want to send these recommendations to my son sitting there. He's a high schooler right now. With that, we have some future work left, and we already finished enable MMU and also upstreaming Android binder fuzzers. The left is creating more fuzzers and profit. I want to acknowledge to a bunch of people here, Tavi and LKL maintainers for making this project possible, and also this person really inspired us to start with libFuzzers. And lastly, pKVM and the binder team for helping us fuzzing these two areas and help us understanding how it works. Lastly, there's some resources. If you want to take a look, I will share the slides afterwards, and so you can get links. Yeah, that's it. Any questions?
Do we have time for questions? Yeah, looks like we have a few minutes, if there's any.
Yeah, there's one.
So I see this is a very valuable tool to be able to do your fuzzing users. But have you done anything to validate that the fuzzing results you're getting in Userspace in any way match the fuzzing results you get if you actually did it in the kernel?
I see. So the question is there any results validating that the fuzzing user space is better than fuzzing in kernel? Is that as good as in kernel? We didn't explicitly verify the result. We're more like, okay, looking into scenarios, think, okay, this one seems to be easier. I think there are things it's probably not easy to fuzz, like the binder fuzzer Eugene mentioned that we don't have a lot of coverage with the syscaller running, and with LKL fuzzers we can get a little bit higher coverage from there. Yeah, I think the goal for this one is not to create something as good as or better than syscaller. It's more like, okay, now there's alternatives. There's new approaches they can use for a specific set of problems.
I would like also to add to this answer is, well, indeed, like we had quite a few false alarms when, for instance, we were fuzzing HID with UHID because we were taking a different path, and some test cases generated like they cannot be like reproduced, like in theory, like using this threat model of a USB device. And I think UHID is a kind of like privileged device, or like in Android, arbitrary untrusted application cannot do this. And the second point is that I think there are different interests from different users of the fuzzing. Like, for instance, we as like internal hackers at Google, we're interested in tools which are so basically, we're okay with it providing a little bit more false positives to us, because what we really want to do, we don't want to miss true positives, and we are okay with handling false positives, triaging them. I think the situation is different for developers. I guess developers really don't want to get distracted by false alarms, and if the issue is reported, is very likely true positive. So I would say that, yeah, it's probably maybe, I don't want to say, yeah, maybe a tool for those who really want to hack on the kernel, find bugs, and are okay with paying an extra effort of validating and triaging bugs.
The question is, have we thought about using this for hardware testing? I don't think we have done anything with with actual hardwares.
Yeah, so are you speaking about your testing the kernel drivers which work on a specific hardware, or? Yes, I think this is actually we particularly cover with Virtio, because in this case we're kind of like mocking out the actual physical device, which is built on top of the PCI bus, and we also implemented fuzzing of other devices which are PCI devices in the overall platform architecture. So we're essentially LKL, it implement support for PCI bus with just a single root port, and the only thing you need is to basically implement its Virtio, not Virtio, its PCI configuration space, and basically implement these callbacks when they will be called when you are reading some specific devices. So I think this is totally usable, and this is exactly how we use it to fuzz the other side of the kernel, which are interfaces with the untrusted hardware. It is a little bit of like extra effort, I would say, comparable to your fuzz in the other direction, where you have like a lot of tools available, because in this case we needed to like implement additional support for this specific like PCI device to enable its efficient fuzzing. But yeah, this is something that we're doing, and it can be used that way. Yeah. Well, thank you.
Thanks. More questions? Okay, if not, here this QR code will bring you to our team site with About page, and there's our emails. You can reach to us if you have any further questions. Yeah, thanks, everyone.
Thank you for your attention.